Welcome students to my latest installment video on Special Topics number 2's systematic coverage of a review of Chapter 6 through 8 from General Chemistry last semester. In this one I'm going to begin by teaching you about bond enthalpy. First I have to of course give my disclaimer. Like I have in my previous video, I'm going to probably cobble together a couple of previously existing sets of footage from earlier videos to cover this because a lot of this material has already been covered. Hopefully that's not too obnoxious to you. Please ignore the fact that my hairstyle and clothes change occasionally. Hopefully it will at the very least be actually entertaining. Alright, so let's go ahead and begin. So bond enthalpy is a measure of how strong a bond is.
We can see that illustrated in this table. For example, a carbon-hydrogen bond, when it is combusted, gives off 413 kilojoules per mole per carbon-hydrogen bond. Similarly, a carbon-carbon single bond is worth 348 kilojoules per mole, while a carbon-carbon double bond is worth 614. Not surprisingly, a carbon-carbon triple bond goes up to 839. This table becomes the bread and butter of the ensuing problems that we'll do. Before getting to that, however, I want to show you some more theory. We can use bond enthalpies from the previous table to estimate overall reaction enthalpies of different reactions. All we have to do is figure out what kinds of bonds and how many of them are broken in the reaction, and what kinds of bonds are formed. Then we just do math to calculate the overall reaction enthalpy. For example, if we were asked to calculate the reaction enthalpy, which is often abbreviated as delta H sub Rxn for reaction, of the transformation shown here, we could summarize it as follows. In this transformation going from left to right, you'll notice that this hydrogen bonded to this carbon is ultimately being replaced with a chlorine bonded to the carbon, and this chlorine bonded to this chlorine is being replaced by a hydrogen bonded to a chlorine. We can thus say that going from left to right in this reaction, we break 1 mole of carbon-hydrogen single bonds and 1 mole of chlorine-chlorine bonds. As we go to the product side, we end up forming 1 mole of carbon-chlorine bonds and 1 mole of hydrogen-chlorine bonds. The full enthalpy of this reaction is then calculated by subtracting the combined enthalpies of the bonds formed from the combined enthalpies of the bonds broken, according to this equation. For our previous example, that would be the sum of the enthalpies of a carbon-hydrogen bond and a chlorine-chlorine bond, and then subtracting from that the combined enthalpies of a carbon-chlorine bond and a hydrogen-chlorine bond. Using the table I showed you before, we can get those numbers as being the following, and determine that the overall delta H for this reaction is negative 104 kilojoules, which means that it's an exothermic reaction.
That takes us to some glorious questions, beginning with this one. Using table 8.4 from the back of our text, and I also happen to have shown it earlier in a slide, calculate the delta H or change in enthalpy for the following gas phase reaction. Now I'm not going to answer this for you here, but I will post a link to a separate video in which I do that you're welcome to watch if you'd like to help guide you through how to do this. Here's another one. Using the same table from the back of our text, calculate the change in enthalpy for this gas phase reaction. Similarly, I'm not going to answer this question here, but we'll post a link to a separate video that can help guide you through it if you'd like to watch it. Alright, that takes us to the end of this video. Please stay tuned to the next one, in which I'll begin by teaching you about Lewis structures. Until then, have an enjoyable rest of your day.